Okay, welcome back once again. Chemistry 3202 course overview, Unit 1, Section 1, Lesson 4, Catalysts and Reaction Mechanisms. Here are the textbook readings if you want to read further into this topic, and there are a few selected textbook items that relate to catalysts and reaction mechanisms. Here is a list of the outcomes that you'll be covering in this section. A reaction mechanism is simply stated as being a series of steps that make up a chemical reaction. And the idea behind this is that reactions should proceed in a series of two-molecule collisions. We want to try and make the collisions as simple as we can, because having more than two molecules complicates the equation significantly. You know, if it's hard enough that we have the collisions with sufficient energy and the correct orientation, that's very difficult that all three of these come together at the same time and everything is met. But if we start to complicate that by saying instead of just having two, now we have to have three or four all coming together at the same time, all with the same energy or the correct energy, and all colliding with the correct orientation, that's a very tall order to fill. And chances are it probably doesn't happen that way. So a reaction mechanism is based on the idea that everything is going to be a series of two steps or two molecule collisions, and we're going to break it down into simple steps. Okay, and in this idea then that the two steps are going to involve the two reactant molecules. Okay, if we look at this reaction down below, it says an overall reaction. What they've done here is they've come up with a proposed mechanism for this particular reaction. Okay, and they say this is going to occur in two steps, and we're looking at this and we're saying, okay, we need to be able to combine these two steps because we want to be able to make sure that there's nothing left over when step one is finished and then step two leads into that. We have to make sure that all we're going to be left over with is what's in the overall reaction. So in this particular setup here, what we're going to do is we're going to start crossing out things that are on the left-hand side and the right-hand side of the arrows. All right, so in step one, that oxygen molecule is a product, but in step two, it's a reactant. So it's just like algebra, you know, 2x on one side, 2x on the other side of the equal sign. You can cross them out because it's the same thing on each side. So we can cross that out. So that part of the equation crosses out, and what we're going to be left with, of course, is when we start combining this, we see there's 2N2O. We can see that there's going to be 2 nitrogen on the product side. There we go. And we're going to be left with a single oxygen molecule right there, and indicating that there's 1. So we're saying then that this is probably, or could be, a valid mechanism that this reaction goes through in order to be successful. So because everything crosses out and everything combines here to get the overall equation, and because we've simplified the steps here and saying, okay, this one should be easy enough because it's only a single molecule that's breaking down, no collision necessary. This step 2 here is involving a molecule of N2O and an atom of oxygen. So that's 2-molecule collision. That's likely. All right, so this is an overall reaction here. And that's how we're doing it. All right, each step in this process is called an elementary step or an elementary process. Okay, and in this case, the oxygen that gets crossed out takes a special name. It's referred to as a reaction intermediate because it doesn't exist in the overall reaction. It disappears, so to speak. As soon as it's produced in step 1, it's immediately consumed and it's gone. It doesn't show up in the overall reaction. Now, don't confuse this molecule of oxygen, this atom of oxygen, with this molecule of oxygen, right? Two different species. This guy disappears, right? It crosses out. So we would refer to that as a reaction intermediate. Okay, here's another reaction mechanism. Now this is a lot more complicated, and we want to bring in some ideas here now of rate determining steps here. And we're saying the overall speed of this mechanism is going to be controlled by what's called the rate determining step. One of these steps in this mechanism is going to determine or control how fast the other steps can go. And it's quite easy to find out which ones, and generally we give you this information. The one that's going to control how fast everything else can go is going to be the slowest step. So right off the bat, by definition, step number 2 here is the rate determining step. So this guy is going to act like a bottleneck effect. Because this is the slowest step, nothing else can go on until step 2 is finished. Step 3 and step 4, they can't do anything because until step 2 is finished, it requires HOBR in this step 3 here in order for step 3 to continue. Until HOBR is produced, step 3 can never be allowed to go forward. So this is going to be the bottleneck where everything waits on step 2 and says, all right, we're waiting for you, we're waiting for you. When step 2 decides to complete, then steps 3 and 4 go bang, bang, right, really fast. So steps number 2 there is the rate determining step. That's the step that controls how fast we go. Okay? Now we want to be able to figure out which are the intermediates. Now I revealed that slide too quickly there, but let's look at which ones are the intermediates and which ones are going to be reactants or products. So in this particular reaction, we can see that the HOBR can cross out right there because that's on opposite sides of the arrow. Okay. HOBR, there's 2 there and there's 2 there. I'm going to cross out those guys. And that's about it. So what I'm left with here then at this stage is going to be 1 HBr and there's 3 more right there for a total of 4. I've got an oxygen that remains right there for 1. And then I have 2 waters right here. Excellent. And then finally I'm left with 2 bromine right here and 2 bromine. So the question would be then, is this a valid mechanism? And the answer could be, all right, possibly. I know that the overall reaction is not going to happen in one step, because you've got 5 molecules that would have to collide all at the same time. That's not likely. So that this reaction probably goes through a mechanism. Is this mechanism good? Well, everything crosses out and combines, right? So there's nothing left over. And the idea behind the 2 molecule collision, 1 molecule, good. 1 and 1, good. 1 and 1, good. 1 and 1, good. So this is a potentially valid mechanism. This could be the sequence of steps that this reaction would proceed. Now getting into the idea of slow and fast and the rate determining step, we want to look at an energy level diagram here. And we're saying now that, yeah, okay, this reaction can undergo an overall big old bump to go from point A to point B. So that's the energy barrier. Remember, that's the activation energy that this reaction has to overcome to get to the other side. Now, the question with this is, well, if it goes through a mechanism, then what happens is each mechanism by itself is going to have its own energy barrier. So in this particular reaction, the first energy barrier is really quick. So that's probably going to be a little bump like that. But the second reaction is a slow reaction. So that's going to have the biggest bump, because that's the one that's going to control the rate of the other one. So nothing else can go forward until we get over that energy bump for number 2. And then energy bumps numbers 3 and 4 are relatively easy. So in this particular reaction, we say 1, 2, 3, 4. Now I don't know the relative sizes of, say, 1, 3, and 4. All I know is that number 2, because it's the rate determining step, number 2 is the highest, and it's the one that controls everything else. So even the overall reaction does not happen until step 2 is completed. So step 2 would be the highest barrier point of the mechanism. So lots of bumps and humps here, and it doesn't matter where these guys are in relation to the others. 1, 3, and 4 are really insignificant. Number 2, because it's the slowest, is the one that matters here. Okay? So each step in the mechanism has its own specific activation energy, and the highest one belonging to the lowest, slowest step. Okay? There we go. Here's another hypothetical reaction. We're saying, okay, we don't know what the overall reaction is this time. All we have is the 4-step mechanism, and we want to be able to figure out what the overall reaction is. So this should be easy enough. We simply say, all right, let's start crossing out things that are on opposite sides of the arrow. So the G can cross out. The S's can cross out. 2 there and 2 there. What else can cross out? The X's can cross out. Now there's 3 on that side. There's 3 on that side. Is there anything else that can cross out? The A's. And that's about it. So what I'm left with then is 2C plus 2R gives me 2W and an M, reactants and products. So there we go. So I've just determined the overall reaction, and I'm saying, yeah, this is probably going to have to undergo a mechanism because we got 4 molecules that require to collide, and that's going to be unlikely. Now, steps 2 and steps 4 may not be likely either, because this is involving a 3-molecule collision, and this is involving a 4-molecule collision here. So that mechanism, although it crosses out and gives us an overall, it may not be a good mechanism because steps 2 and 4 are probably a little bit unlikely that they're going to happen. Okay? When we look at this, we say, well, which ones are the intermediates? And we look at this and we say, well, there's lots of intermediates now. Anything that crosses out there, anything that is produced and then consumed is going to be what's called an intermediate. So G, S, and X are going to be intermediates because they get produced and then immediately get consumed. Now there's a new thing coming up here, catalyst. A is representing a catalyst, and we're going to talk about that now in a second. Okay, so there we go. If I was going to do an energy profile diagram, assuming that this is an exothermic reaction, what we're seeing is that this is going to go through a series of 4 steps, and because step 3 now is the slowest step, that's the one that's highest. So the overall reaction would look something like this, with the highest energy barrier being at step 3, because step 3 is the slowest. That's the rate determining step. Okay, here's another chemical reaction. Quite quickly we'll go through this. We'll say, all right, is this a valid mechanism? Well, the fluorines can cross out right there. That's F minus, and that's it. We're finished. So we got 2NO2 right there. We've got a fluorine right here. And we've got 2. So good enough. All right, so that's the intermediate is F because that's the one that gets crossed out. Now, again, don't confuse F atom with F molecule. F and F2, they're 2 different species. All right, what would this graph look like? Well, it's going to have 2 bumps because it's a 2-step mechanism. And we know that this is going to be exothermic because this is a negative 284. So we're going to be releasing energy. Energy is going to be lost in this process, and it's going to be a 2-step bumps or 2-step mechanism here. So we're going to see something that looks like this. It's a little messy, but we can see here that it's exothermic, so it's a minus 284, so energy is released as this reaction goes forward. All right, so energy is going to be released as this reaction goes forward. It's a 2-step mechanism with the first step being the highest one because that's the lowest activation energy. So if I was to do this as a overall reaction, for the overall it would look something like this. And again, the highest step is right there. So that's the highest energy barrier, so that's the rate determining step. There we go. Okay, we want to look at something called catalyst, because remember we referred to A on the other reaction that we just did as a catalyst. And we know from previous work with reaction rates that we can add a catalyst to a chemical reaction, and it speeds up the reaction by offering another alternate energy pathway. Aha! Eureka, bell should be going off here now. When we add a catalyst to a reaction, what it's doing is it's providing an alternate set of steps. So the reaction may proceed through one set of steps that takes a lot of energy, but when we add the catalyst, we can provide a new set of steps which is going to have lower energy requirements. And that's how the catalyst is going to work. So if we look at, we can identify which one's the catalyst, because remember we said before, when we add a catalyst to a reaction, the reaction speeds up, but when the reaction's finished, we can reclaim and reuse the catalyst over and over and over and over again. So in this regard, we have to say that if something is being added to the reaction as a catalyst, then that catalyst should be recycled somewhere further along the lines in this particular mechanism. So let's go back and look at this example. All of these guys were crossed out, but if you look at G, G was produced and then consumed. It disappears. S was produced and then consumed. It disappears. X was produced and then consumed. It disappears. Look what's happening to A. Even though we crossed out A was consumed in step 1, but then it was recycled again in step 2. So technically speaking, what we like to do with A is we like to write it over the arrow and say, in order for this reaction to proceed according to this mechanism, A is required as a catalyst. It's not involved as a reactant, it's not a product, but it's required to get this reaction moving faster. So A would be consumed in one step and then recycled in another. Okay, if we look at a mechanism for this guy, we're saying that, okay, this particular reaction normally does not want to chemically react, but when we add a catalyst to it, the reaction flies. And what they figured out for this guy is to say, okay, well, this is the mechanism for the catalyst, and we want to figure out now what was the catalyst that was added here. Well, if we look at this particular reaction, this guy and this guy crosses out. That one and that one crosses out. And what we're left with is we're saying, yeah, the hydrogen can cross out because it's on opposite sides, but unlike the red ones there, the hydrogen is consumed and then recycled and produced again. So this reaction mechanism depends on the addition of an acid catalyst. Okay, the reaction mechanism now for this catalyst would be a lower energy level, and it would go through three steps, so 3 bumps, 1, 2, 3. Step 2 would be the highest bump, but you notice what we've done here? This bump here now does not go up to the overall reaction again, because what happened is the catalyst had lowered the energy requirement. So in the other examples we were doing, the highest bump always went to the top of the overall reaction. But in this case over here, because it's a catalyst, the energy is going to be much lower than it normally would have been. So this particular reaction mechanism, I'm showing you in a dotted line, that overall requires less energy than it normally would have. All right, so that's what the catalyst does. It lowers the energy requirement, makes it easier to go forward, and therefore it's going to be quicker. But again, it's still going through the catalyst is going through a mechanism that involves 3 steps, and step 2 is the rate determining step. The intermediates here, these guys are the ones that are produced in one step and then consumed in another. They disappear. And the catalyst is the species that's consumed in one step, and then it's produced or recycled in another step. And there we go. And because this guy is an endothermic reaction, it's a plus 72.8, we can see that this is where the energy that's going to be absorbed is a plus 72.8. It's an endothermic reaction. The addition of the hydrogen catalyst allows the reaction to proceed much more quickly than it normally would. Okay, here's another one. This one's ozone depletion. And this is a reaction of the depletion of ozone in the upper atmosphere. And the ozone is O3. And in the presence of UV light, it produces oxygen. And you might say, well, that's a good thing, but not really, because this is high-level stuff going on here. This is up in the upper atmosphere, and the upper atmosphere ozone is what blocks out the ultraviolet light, which protects us from getting severe sunburns and protects the earth from overheating and all that stuff, and it harms our eyes. If the UV light gets through, then it harms our eyes and all that stuff. So this O3 protects us by absorbing the UV light and converting it into oxygen. Now, one of the things they noticed is that back in the 60s, 70s, and early 80s, they noticed that the ozone layer was beginning to deplete. And what they found was they discovered that the presence of chlorine-free radicals in the atmosphere from things like CFCs, chlorofluorocarbons, so from propellants, air conditioners, fire extinguishers, fridges, freezers, and the like, was releasing chlorine into the atmosphere. And they came up with a mechanism, and they said, well, this reaction really does not want to happen. It takes a lot of energy in the upper atmosphere for that to happen, special conditions. But what they found was that the presence of a chlorine free radical, that's what that little dot represents, a free radical, catalyzes this reaction to make the reaction go faster than it otherwise would. So what we're seeing here is that the chlorine sure does cross out, but look what happens. It's consumed in step 1, and then it's recycled in step 2. So it's acting as a catalyst. Okay? The ClO in this particular reaction is produced and then immediately consumed. It disappears. That's going to act as an intermediate. And I've got that multiple choice questions there. There we go. Number 2, which is the catalyst? Well, we now know it's the Cl minus. Which is the rate determining step? That's easy enough. It's always the slow one. And if we were to do this chemical reaction as an energy level diagram, we say that, well, this reaction really doesn't want to happen normally. So it's going to be a really tough reaction to go. So it's going to have a very high energy kick in the overall. But what happens is, of course, we got this great big high energy kick, doesn't want to go forward. But as soon as we put this chlorine-free radical here now, it lowers the activation energy. And what we normally like to do here is we like to do a dotted line, like this, showing you that this lowered energy here is the effect of the catalyst. All right, so the chlorine allows this reaction to proceed much more easily than it otherwise would. Okay, here's another one. It says, consider the elementary process here. We want to write the overall reaction. Okay, shouldn't be a problem. We can start looking at this and saying, okay, NO is consumed and then recycled here. Ooh, that's a special one. So that's probably going to be the catalyst, the NO. The NO2 up above is being produced, and then it's immediately being consumed. So that's going to disappear. So that's going to be the intermediate, NO2. The overall reaction here is going to be O3 plus O gives me 2 O2s. It says the uncatalyzed reaction is a slow exothermic reaction. Slow exothermic reaction. So if we do an energy level diagram, we're going to have a reaction that's going to produce energy, so it's going to start high and end low. And we want to be able to sketch the uncatalyzed reaction, and then on the same graph, sketch the catalyzed reaction. So here's what it's going to look like. So if this guy is a exothermic reaction here, we can see that the energy is going to be released as the reaction moves forward. It's a slow reaction, which is an indication that it's going to have a very big bump here. The higher the bump, generally the slower the reaction. And this would be the uncatalyzed reaction. The catalyzed reaction mechanism is going to be a series of 2 bumps, with the first bump being the highest. And the overall effect, of course, is a lowering of the energy requirement. Okay, last but not least, another public exam type question. It's saying that this reaction is very fast at room temperature. And they're proposing, a student proposes the 2-step mechanism, saying this is probably how this fast reaction occurs. And they're saying, do you agree or disagree with this proposed mechanism? And the answer is why. Okay, the very first thing we have to do is say, all right, does these 2 steps, can we start crossing things out and combine step 1 and step 2 to make the overall reaction? And when we do this, we find out that, you know, we can cross out a hydrogen here can cross out. The H4O2 plus crosses out. And that's what we're left with. Okay? So we're left with H and I minus, H2O2, H2O, and HIO. Well, this is the overall reaction. So yeah, so far so good. We can combine it and everything works out. The problem with this mechanism is the fact that step 1 involves a 3-molecule collision. And we don't like that for mechanisms, all right, because a more valid mechanism would involve only 2-particle collision. Step 1 is involving 3 particles that have to collide in a line and all have the correct energy. Very unlikely that step 1 would happen. It may happen. No one's saying it wouldn't. But it's very unlikely because it's more likely if it was only 2 molecules. Like step 2 is likely because it's 2-molecule collision. Step 1, possible, but unlikely because it's 3 molecules that would have to collide, all with the correct orientation, energy, and they'd have to collide at the same time. Okay, there we go. So that's reaction mechanisms.